Okay, so let's start. Good morning, everyone. I'm Marianne Foizel. I'm professor in ECE, and I'd like to welcome you to the new quarter and to the ECE Colloquium. This quarter, our colloquium has gone through a lot of changes, and it is going to be led by Professor Sam Burden, who's also our speaker today. And he will tell us more throughout his talk about how the series is going to work and the topic of the whole colloquium series. So let me introduce our speaker. Sam Burden actually earned his bachelor's degree from our own department in 2008. He's an alumni of our own department. Then he moved to get his PhD degree from the ECS department at UC Berkeley in 2014. He also did a year of postdoc work there in Berkeley, and in 2015 he returned to UW as an assistant professor. In 2016, he has received a Young Investigator Award from the Army Research Office. His research interests in general are in robotics, especially sensorimotor control and dynamic and dexterous robotics, as well as cyber physical systems more generally. One interesting thing about Sam is that today is his birthday as well. So happy birthday, Sam. And we look forward to your talk. Please take it away.
Okay, super. Thanks so much for that wonderful introduction, Mariam. Yeah, happy birthday to me. It was pretty serendipitous that I got to schedule the whole colloquium and then choose the speaker on the very first one. Happened to be me. So I'm really thrilled to be able to talk and present my work to you folks today, and kick off this colloquium and also introduce the whole theme of this colloquium and talk just briefly about the awesome lineup of speakers we have. So broadly speaking, this talk and really the colloquium topic is, very selfishly, I got to choose this around my research interests and themes, and those are these two threads of contact-rich dynamics of robots that are locomoting or manipulating or interacting intermittently with terrain and objects in the world, and then human-in-the-loop control systems and more broadly sensor-motor control in squishy systems like people. So the kind of broad leaping off point for these threads of work is the observation that increasingly, human interaction with the physical world is mediated through machines. And these are not like the passive machines of yore or the simple machines of, thousands of years ago. These are machines that are intelligent, have perception, have learning or adaptation or artificial intelligence kind of mechanisms built in. And they're really, pervading all aspects of our life. So three examples from kind of recent progress that I find particularly exciting. First example is this idea of robot-assisted surgery. This isn't as new as the other ones, but this continues to have a growing impact in like actual clinical surgical practice. So, Intuitive Surgical, the company that first held the patents for these, deployed, I think, on the order of like 1 million units. And there are surgeries being performed all over our city, state, and country and world with these things every day and improving surgical outcomes. And more futuristic techniques, maybe some of this will become more automated or be able to apply and improve outcomes in other types of surgeries and things like that. Another class of examples is using engineered systems to restore function or mitigate the effects of disability or disease or injury or neurologic kind of pathology or something like that. So the example here that I'm highlighting here, Jan had an injury maybe 10 years ago spinal cord injury that made her unable to control her body from the neck down. But researchers at Pitt, by implanting electrodes into her motor cortex and then interpreting the electrical signals that come out of there, are able to enable her to control a robot arm to do something that I think probably everybody on this call takes for granted, which is just the simple activity of daily living, of being able to feed yourself, have that level of autonomy in your life, to be able to do something as simple as enjoy one of your favorite snacks, chocolate bar in this case. But even in health, so even without having an injury or disease or something like that, there are devices that are increasingly enhancing or augmenting natural human ability. So the example I'm highlighting here, now it's a little bit older, 2015, but it's a completely passive, so there's no battery, there's no computer in the conventional digital computer sense, a completely passive ankle exoskeleton that reduces the metabolic cost of walking for just typical, kind of healthy population by multiple percentage points. And you look at that and you think, well, I've shaved off a couple of percentage points of efficiency and metabolic cost of walking, big deal. But if you think about the fact that one of the leading theories of why people evolved to become bipedal is that we would literally walk our prey to death. So we would cover just large spans of the savannah, going after our prey and things like that. The fact that a completely passive device, again, no battery, no actuators, can improve upon that evolved system by multiple percentage points, I think just indicates that we've only scratched the surface of the potential for these augmentative technologies. And the broader point that I'm raising by this specific choice of examples, because there are a lot of other machines in daily life. My car has a certain amount of automation built in, and you can, if you go to the Bay Area or you go to Arizona where it's sunny, you can ride around in a car that drives itself and things like that. So there are certainly cases where automated machines will completely supplant kind of human role and human presence and things like that. But I think there are many applications, and the three that I listed here are three key ones, where for a variety of reasons that fall outside the technological, even if we could overcome the technological limitations, people are going to be critical components of control loops in a lot of systems for the foreseeable future. So I'm interested in those kinds of applications where we're not just going to completely replace things with autonomy. So those are very broad set of applications. So for the purpose of describing my research and even just grounding this discussion a bit more in a more specific set of examples, let's think about the problem of robot teleoperation. This is kind of nice because it has the human in the loop, but it sort of pulls the human and the machine apart so that we can cleanly design and reason about the interface between them, and they're not sort of necessarily physically directly coupled the way they are in those other examples. And so the basic idea, if you haven't seen this picture of robot teleoperation before, is that we have some interface, mechanical, digital, display, thing like that, that's recording information from the human. So they have a joystick, or they have some other fancier interface, an example of which I'll talk about in the second part of my talk, providing input to the robot. And the robot is in the same room, or it's across the hall, or it's away in a field somewhere. So it's a remote robot. And then that robot is providing back some sensory input that's displayed to the person in a variety of ways. And that could be as simple as a computer display, or maybe a virtual or augmented reality headset, or it could be more fancy like a vibrotactile display, a haptic feedback system, or potentially a direct neural stimulation or something like that. And again, robot teleoperation itself is a very big field with a lot of different possible, applications and contexts and things like that. So just to put a finer point on it for the purpose of my research, not necessarily the other people's that will be in this colloquium series, and something that's probably on everybody's mind in recent memory, think about the challenge of what we do when there's like a forest fire. Right now, other than just cross our fingers and hope it doesn't come too near us, what we do is we send in very brave first responders, right? So we might evacuate some subset of the general public, but we immediately put more people directly in harm's way to try to protect our communities and people. And that's the best that we have at this point. But wouldn't it be great if we could pull those people out of immediate danger and replace them with some kind of firefighting robot or something like that, so that even though there might be, maybe that would, if that robot were to burn up in the fire or get damaged or something, that would cost a lot of money to replace, but it wouldn't be a loss of human life. However, if you happen to track the results of a recent worldwide multi-million-dollar robotics competition, you wouldn't want to rely on autonomous robots to do your firefighting tasks or other kinds of safety critical, high operational tempo tasks for the foreseeable future. And I don't like to make fun of the outcomes. I mean, actually, there were really striking successful demonstrations in this competition where, these huge hundreds of pound 30 degree of freedom humanoid or other kinds of bizarro robots were able to coordinate, once they got within the reach of some tool or some task, turning a valve, opening a door, something like that. In many cases, they were able to coordinate all of these joints and these hundreds of pounds of equipment and everything, and integrate, fancy perception systems with optimal controllers and things like that, and execute these full body maneuvers. But even just getting to the task in the first place proved to be a challenge for a number of teams throughout the competition. And if you don't know the background behind this whole competition, I mean, this was multi-million-dollar prizes on the line. There were companies companies and research groups from different universities around the world that competed. And so the takeaway for this is that, we're not going to really rely on those immediately for our firefighting future. But even in kind of more conventional or more familiar applications than this futuristic firefighting scenario, we have to be careful about what happens when we can't just dump people in the middle of an automation loop and expect good things to happen. So the aerospace industry has known this for decades. They have this well-characterized phenomenon they call pilot-induced oscillations, which arises when you're trying to build a high-performance aircraft. You're designing it so that it's, and its low-level control and its physical design, so that it's kind of nearly unstable. It's right at the margin of instability, or maybe slightly unstable, and you rely on the pilot to stabilize and control the maneuvers of the thing. However, if you fail to take into account the fact that the pilot itself is a biological system that has fundamental neuromuscular delay, visual motor delay, then those delays, once they're incorporated into your kind of tight, nearly unstable feedback loop, can cause instabilities. And this has actually led to the crash of multiple test aircraft. So imagine, you're working at Lockheed or Boeing, and you've spent 5 or 10 years designing the next generation fighter craft or something like that, or rotorcraft. And then the very first test, you go out there, it all works great in the wind tunnel and all of your benchtop tests, and you go there and put the pilot in there, and they have to abort and eject because you didn't take into account their biological reality. So this is something that's been really well studied in that field, and still an issue that always has to be taken into account. Kind of more recent example that more of us may have firsthand experience with is the inclusion of so-called enhanced safety features in automobiles. So I actually have a brand new car, and it has these features built into it, and they're really lovely. But especially at first, it was an adjustment for me, to say the least. There are these flashing lights, they have cameras looking at me, and they're telling me, oh, you're not watching the road. But then when they tell me that, then I'm distracted looking at the dashboard and not actually looking at the road. And so there's actually a funny statistic buried in this report that came out of an insurance industry association a couple of years ago that had statistics that suggested that if you had some of these enhanced safety features in your car, you were actually statistically more likely to be in an accident. So from the insurance company's point of view, you would have paid more money to get these features installed if they didn't come standard, and then they should charge you more money because you're more expensive to insure. Now, I don't think that's the case anymore, and this seems like it might be an example of something similar to what happened when like anti-lock brakes were introduced in the 70s or something like that, and people fundamentally had to change the way they drove. They had to adapt to that new low-level automation to drive safely in slippery conditions. And so we may be in kind of a similar situation now, where maybe now truly these enhanced safety features are better. Actually, I have indirect evidence of that, which is that even though I went from a 2011 Ford Focus to a 2020 Subaru, my insurance payment stayed the same because it costs way more to insure the physical part of the car, but it's costs way less to cover the liability insurance. So at least according to that insurance company, it's much safer to drive my current car with its safety features. But the point here that I'm trying to drive home is that we can't just dump people into the middle of automation naively. We have to consider the dynamics that the person brings into that feedback loop to engineer things safely. So returning to this big picture, the broad question that's motivating a lot of my research program here at UW will be the topic for the rest of the talk, and really is, I think, the overarching theme that I tried to assemble for this whole colloquium is: how do we enable people to learn and control the dynamics of robots that are interacting intermittently through contact with the environment? So to give kind of just a brief high-level picture of what the rest of this series is going to look like, I basically got the charge from Professor and Chair Eric Clavens to design the colloquium, invite speakers that I wanted, basically people that are my favorite people in my field. And one of the few benefits of being, in kind of travel restrictions and lockdown and pandemic and things like that is that it's much easier for people to say yes to a virtual invitation than a physical invitation that they have to travel to. And so I got everybody that I wanted. So these are the, I could add another 10 if I had another 10 slots, but these were my top people that I wanted to hear from. And with the exception of Ram Vasudevan, who's a collaborator of mine, a long-term collaborator of mine, we were grad students together at Berkeley. These are all people that are, leaders in my field that I've been looking up to since I was a grad student, and I'm really thrilled to be able to share all of their work with you folks and with your community. They span all kinds of different areas, from neuroscience to robotics, to rehabilitation, to micro systems and micro robotics and things like that. And we have several leaders in industry, people that are CTOs of various technology companies or research labs in industry. So I really think that there's something here for almost everybody, if not everybody, in our broader ECE community. And I'm just really thrilled to be able to, again, share these people and their work with you. Okay, so that's the conclusion of the high level pitch and the intro. So now we're going to dive into technical details. I'm happy to, we have 133 people signed in online, so we probably can't, turn this into a completely free-form discussion, but I'm happy to take questions as they come up. So I've got the chat window here that I'm monitoring, and I've got the participants window. So if you want to, raise your hand or do an emote or something like that, I'll try to look at that and call on you, and maybe Emily can help me monitor this as well, if she's able. Or I think that you're able to unmute yourself and just start interjecting and asking a question. So I invite you to do that as well. Again, if it gets too out of hand, we may have to tighten tighten things down. But I'm happy to make this interactive, as opposed to me just talking in my default mode, which is very quickly through a lot of things very quickly. Okay, but with that kind of disclaimer, I think we'll go ahead and dive in. Like I said, I have these two broad themes in my research program. And so I'm going to structure the talk kind of parallel to that. And then hopefully you'll see the way these things kind of interconnect by the time we get to the end. So the first big topic is understanding the contact-rich dynamics of robots that are locomoting with legs. So if you haven't thought about this before or seen this this kind of reasoning, you may think, well, okay, yeah, I'm moving with legs on the ground, but that's basically the same as, if I was swimming or flying. But actually, there's some kind of fundamental differences and actually fundamental gaps in our knowledge. So in the case of hydro and aerodynamics, even though they're complicated, they're governed by nonlinear PDE, infinite dimensional dynamical system, at least there is the PDE, at least there is the Navier-Stokes equations, the fundamental constitutive laws that describe how that physical system behaves. In the case of legged robots that are intermittently slapping their, or animals that are intermittently slapping their legs on the ground, we don't have an analogous first principles sort of theory, and there's kind of an emerging empirical phenomenological collection of rules. But the key observation, I think, underlying all of this is that, when I'm immersed in a fluid, I'm sort of always exerting forces and having forces exerted on me when I move my body around. But when I'm doing legged locomotion, neglecting air resistance, I'm really only I really only have control authority, and my dynamics are changing dramatically as I make and break contact with the environment. So from a modeling point of view, I'm a control theorist by training. That's been my specialty from undergraduate here at UW through grad school and back now as an assistant professor. So from a control theorist perspective, I like to think of what is a reasonable class of descriptive but parsimonious models for the physical phenomenon I'm interested in. And so the class of models that I have focused on for the last 10, 15 years are so-called hybrid dynamical models, and more specifically in recent years focusing on the specific structure we get when we have mechanical systems. So we have legged robots or legged animals. And so the flavor of the mathematical model, I just want to give some of the details because it'll help inform our understanding of the theoretical results we have in this area. The flavor of the mathematical model we have says, okay, I have some number of limbs that can contact the ground. Associated with each of those limbs, I have a non-penetration constraint that says my leg can't go below the ground or it can't penetrate the object I'm trying to grab. If I have a collection of limbs in contact, in a given contact mode, then there's, standard F equals ma. There's just Newton-Euler Lagrangian equations that govern how the system evolves. Importantly, the ground exerts reaction forces that enforce the non-penetration constraints, so it actually augments the dynamics in every different contact mode. And then, moreover, if I want to maintain these non-penetration constraints, if my foot is going down at the ground and it reaches, zero height with non-zero negative velocity, then something needs to change rather quickly Otherwise, my model is going to violate that constraint. And so what we do in this modeling paradigm is we say, okay, we will permit instantaneous resets or discontinuous updates of state when certain events happen. In the case of these contact dynamics, it's going to be, as I make and break contact with the environment, I could have a discontinuous change in state, and I could have a corresponding discontinuous change in the forces. So that's kind of the symbolic language of this. Now I want to introduce a bit of a visual language that I'll use to illustrate concepts throughout this part of the talk. Start with the simplest system that I basically built my whole PhD around, which is the model that hops in place. It's a vertical hopper. So I have two masses, they're hopping up and down. And graphically, visually, what you should imagine is that starting from some position and velocity, I follow my continuous time F equals ma dynamics until my foot hits the ground. So A of Q equals 0. At that moment, my velocity instantaneously resets, and then I continue flowing as before. And you might look at these dynamics and think, gosh, they really look like they have this big striking discontinuity in them. But one of the early results, of course, it was the Russians that figured it out in the 50s, is that even though there is this jump discontinuity in the middle, if I think about how trajectories vary away from moments of impact, then you can actually get very reasonable dependence on initial conditions, by which I mean the initial state, but I could also lump in parameters and control inputs and other kinds of information like that. So for instance, if I perturb away from my initial state in the red or the blue directions, and then I go to my final state, final time t, which is not an impact time, then the way the final state varies will be continuous and actually classically differentiable with respect to that initial state. This seems kind of counterintuitive, so I'll just state the theorem, give the reference. But it's basically, look, even though there is this jump in the middle, the overall process of flow to the boundary, then jumping, and then flowing again, composing all of those together mathematically gives me a smooth function. So I get this differentiable dependence on initial conditions. Again, this result's been known since the 50s. I'm a member of a long line of people who have rederived this result in various contexts, so I won't tease them too hard about that because I'd be teasing myself. But the point is that when you know the sequence of contact constraint activations and deactivations, you get this smooth dependence on initial states. So a big question that my group is focused on is what happens when that sequence of contacts can vary. So I have in the top here a video of a 6-legged robot that came out of the lab that our professor and chair Eric Clavens did his PhD in, 6-legged Rex robot that runs like a cockroach. So it uses an alternating tripod. 3 legs are coordinated and anti-coordinated with the other 3 legs. A more familiar kind of behavior is the bound of this quadruped robot, where the front 2 legs hit the ground at the same time and then the back 2 legs hit the ground at the same time. But these are the nominal behaviors, right? If my hexapod or my quadruped get perturbed at all, so the ground's a little uneven, an actuator kind of, or a sensor kind of, blips for a moment, or we go up and actually kick the thing or something like that, then the feet will in general fall in different sequences. And the question is, what happens near those kinds of events? And the answer is actually quite troubling in general. So in general, if I build my robot in a conventional way, which is assemble a bunch of rigid struts together to make a rigid kinematic tree, then actually what happens in going from the difference in these 2 slides is there's only one leg touching down or only one constraint that's activating here, and I get this continuous and smooth dependence, versus multiple constraints, multiple footfalls activating at the same time. And what happens is actually trajectory outcomes get broken apart and they get split into distinct regions of space. This is not a result of ours. This has been observed in the robotics literature a couple of different ways. Here are my 2 favorite examples. One is if I have a rigid object I'm manipulating, and if I have a manipulator that's a rigid kinematic tree. Of course, my hand is not a rigid kinematic tree. It's soft and squishy, but imagine that it was like a rigid robot hand, like from, a 1950 or 1980s sci-fi movie or something. Then here's what the model says. If I have some number of digits, fingers in contact with the object, and then a new one comes in and impacts with non-zero velocity, some subset of the digits have to pop off, and which subset pops off is not uniquely determined. It's basically decided by which 17th century mathematician you trust for your law of instantaneous impact in mechanical systems. So whether you're a Newton fan or a Legendre or an Euler or something like that. And so the point being that if you have these rigid collections of limbs, then you get these inconsistencies in your post-impact state. And just to give a little bit more intuition or a little bit more detail about like mathematically, what is it that happens here that's kind of driving it? When I have this rigid coupling between all of my limbs, then if I think about a simultaneous impact event, I could, you know, by changing the initial condition a little bit, have one impact happen before the other, or them happen in the vice versa in the other order. And when I have these rigid coupling, those two operations don't commute. So I get these two inconsistent outcomes from this same kind of event. But if I have a mathematical condition that I'll give a little bit more intuition about in the subsequent slide, if I mathematically decouple, get rid of this rigid coupling between things, make the limbs compliant or make them very, very light, so nearly massless, then these two operations commute and I get a consistent outcome. So the upshot is the theorem that we proved is that if you have this decoupling between your limbs, so not this kind of rigid constraints that we conventionally build robots, then you actually recover the continuous and dependence on initial conditions. In fact, you get something stronger than that. You get a form of differentiability that's not classical. So I'm trying to illustrate this by saying if visually, if I perturb in the red direction or the blue direction, I still get continuous dependence in the final condition, but the direction at the red direction at the final condition is different than the blue direction at the final condition. So there is a first order approximation in the red and the blue direction, but they're not given by the same linear operator. If you're interested in details, then we have kind of a sequence of papers developing this non-smooth calculus, or applying this non-smooth calculus that was originally developed by the optimization community, and then applying it to these mechanical systems to get these kinds of results. And I really want to highlight this or I want to highlight Andrew Pace's contributions to this result. Andrew Pace is my second most senior PhD student. He's the most senior PhD student in my lab in that he's defending his thesis tomorrow. So he's about to become the second graduate from my group. But he's really the technical powerhouse behind this particular result. So what's fun about this talk is that I get to share with you the work, basically I'll get to highlight work from my senior PhD students and a postdoc that I've had in the group in recent years. So this is all stuff that came out of UW. Okay, so now I have a way to reason about trajectories varying continuously in these mechanical systems that go through different contact mode sequences. And so a natural question is to ask from a control theory or design, a stabilization perspective is, do trajectories contract or do they expand? So do they get closer together over time or do they get further away? And so really this question is not a topological question or a differentiability question the way the previous questions were. This is more of a metric question, right? So if I start at X and Y, and then I end up at XT and YT, am I closer together or further apart than I was before? So before I can make sense of this question, I first need to do a little aside on what I even mean by measuring distance in these systems with contact that have these kind of jumps in state. And I'm gonna make a declaration that at first might seem strange or downright crazy, but turns out to have a lot of really strong mathematical machinery that justifies it and kind of fleshes it out. I'm going to declare, you know what, in my system, if I'm at an impacting state immediately before the impact where the velocity is pointing into the constraint, and then I immediately reset in 0 time to a new state where the velocity satisfies the constraint, I'm just going to declare that the distance between those states is 0. So I'm basically doing metric or topological violence to the system. The underlying machinery is that we take a topological quotient and then we show that the quotient is metrizable and that the metric that we construct in this that's kind of naturally derived from this condition is compatible with that topology. But the key point is that now I'm able to measure distance in this system in a way that's compatible with these instantaneous changes in state that are introduced at the moments of impact. So this is a bit of a technical aside. I really like this result. I'm really proud of this result, and I'm working with some collaborators to extend it now. So I like to at least mention it, but also the subsequent results I'm going to present don't make sense unless you have some sense of what I mean by distance in these kinds of systems. So then the technique that we were able to generalize is a concept called contraction analysis or infinitesimal contraction analysis. So first I'll describe briefly what it looks like in classical systems, meaning smooth differential equations or difference equations, so dynamical systems that evolve in continuous time or discrete time, before I present our result that merges these two and applies to these hybrid or piecewise defined systems. So a notion of infinitesimal contraction and the kind of result you can get. Now, Lohmiller comes from this famous paper by Lohmiller and Slotin. They're not the first ones to come up with the idea. Of course, it was a Russian, Krasovsky, in the 50s or something like that, or 40s. But they have a very nice and famous expository paper that illustrates these ideas, and it's very intuitive, or has very strong intuitive appeal. So I have a nonlinear but smooth system, x dot equals f of x, or x plus equals r of x. And what I can do is check properties of the linearization of the dynamics. Now, this is not linearization at an equilibrium, because the system's time varying. I don't expect it to have an equilibrium. This is linearization everywhere. So I'm looking at the Jacobian of my vector field, or the Jacobian of my resetting map, defined everywhere. And then what I'm doing is checking a linear algebra condition on all of those matrices. Now, granted, this is an uncountably infinite number of matrices, but in some cases you can, special cases, you can actually check these conditions. And if I get a condition on the eigenvalues of the symmetric part of the Jacobian of the vector field, or the largest singular value of the linearization of the reset map, that kind of local characterization of how do trajectories locally or infinitesimally, using derivatives, expand or contract, then I can get a really strong global conclusion about the fact that all trajectories are converging toward one another at an exponential rate. This is an incredibly strong property that systems don't have to have, or in particular, they don't have to have with respect to kind of a natural or obvious metric that you choose for a system. There are sort of converse results that if a system is stable, then there is a metric with respect to which it satisfies this kind of contraction condition. I'm not going to talk about that. But the point that I want you to take from this slide is that there are existing methods that let you go from differential characterization of contraction to full-on, full system characterization of trajectories coming together. And this is exactly what we were able to generalize. Now, we can't just say, I have a piecewise defined system, so I just want to be contractive in continuous time and in discrete time, because in our systems, those dynamics aren't independent, they interact, right? I can't read.
Your audio cut out.
All right, can people hear me again? Can I see some thumbs up? Okay. Yeah, I have this wonderful headset that has good audio, but it also has this funny quirk. So in my class of systems, I can't reset until I have reached the constraint. And similarly, once I reach the constraint and reset, that influences the initial condition for the next stage of the continuous time flow. So the point being that in the class of systems I'm interested in, continuous time and discrete time interact, and you can't just analyze them separately. So I need to consider the interaction between them. So in the most notationally and technically dense slide of the talk, I'll try to give some intuition about what that interaction looks like in the systems I care about. And I'm appealing again to this idea of perturbing off of a trajectory at one time and then seeing after some flow and some reset where the final state gets perturbed. And the point is that if I perturb before a reset, the final state is not perturbed just by the linearization of the reset. I have to take into account the flow before and the flow after. So the values of the vector field immediately before and after the reset as well. In this funny matrix that I denote with S, stands for saltation matrix. This is terminology introduced by the Russians and the French decades ago, but now I think I understand that saltation means like abrupt change. So it's a pretty reasonable term. And the formula is kind of complicated, but the point is that I can't just, I think the point that you can take from it is that I can't just look at the linearization of R. That appears in there, but that's not the only part. I also need to look at how the vector field interacts with the surface that defines the reset function and the function that defines the reset and things like that. Okay, so not that I'm expecting those technical details to you to completely understand. The point is that now I can tell you how we go from this local to global characterization of contraction in these piecewise defined or hybrid systems. We need, of course, contraction in continuous time and contraction in discrete time, but with the asterisk or caveat that I'm looking at this saltation matrix that accounts for the interaction of discrete and continuous to then get this global contraction between trajectories. And an important caveat here is that the distance metric I'm using here is that funny intrinsic one I introduced by doing the violence to the different states of the system and saying the state that I'm at immediately before and after I reset are actually the same state at zero distance. And only with respect to that metric do I get this kind of global contraction condition. Because of course, if those were treated as different states at non-zero distance, then every reset takes states that are arbitrarily close and breaks them apart, pushes them far away. But that doesn't happen in an intrinsic sense. Okay,
hey,
so
Sam, I have a question about that.
Yeah, please.
Can you imagine a situation where you get a sort of cyclic sort of set of constraints about defining this metric that's somehow inconsistent. You know, like the distance between these two has to be the same, and then you flow for a while, and then the distance between these two has to be the same, and you go all the way back to the beginning, and it's like something happened that these two can't be the same if all those other things are going to be the same.
Yeah, that's a great question. Yeah, so let me go back to this slide. So it's definitely a concern, and in particular, you know, I can quotient topological spaces. I can define equivalence relations and declare this is the same as that, and now I get a new space. And then I can also separately define distances, you know, using some rule like this, and then maybe taking using this as the basis to then define a distance. But you might wonder whether or not what I get is a distance function, even like a distance candidate, meaning is it symmetric, does it satisfy triangle inequality, things like that. And then does it have any relation to that quotient topology? And there are definitely counterexamples to all of these things. So our contribution is kind of, you know, several components, which is first showing that the distance function we define based on this rule, or with this rule as the kind of starting point, is an actual distance metric, and that the topology corresponding to that metric is the quotient topology, so it's compatible with that quotient. So it's definitely a valid concern, and there are definitely counterexamples in sort of abstract topology, but by restricting the kind of hybrid system that, you know, the properties of the hybrid system, then we're able to get this kind of consistency.
Sort of follow-up question, Sam.
Yeah.
How does this relate to energy and passivity? Because if you have a little energy loss at the reset, does the distance metric still apply, or do you have to modify it?
Yeah, that's a great question. Yeah, so in mechanical systems, you know, even if they're undergoing impact and things like that, I do have kind of somewhat natural candidates for either distance or like a Lyapunov function, because it's energy, it's total energy in the system. And there's a couple of things that there are a couple ways in which that connects with what we're doing here, and then some ways in which it's kind of distinct. So let me show my example, because I think then I can better address this question. To satisfy these infinitesimal contraction conditions, it's not enough that we replace our rigid links with you know, squishy elastic ones, so spring dampers as like the simplest instantiation of that. I mean, that was necessary to get continuity and piecewise differentiability according to the first theorem. But to get this contraction to happen, we actually have to go to viscoelastic limbs. The reason for that is that the discontinuity in the force in a regular elastic limb causes problems with this analysis, basically. Even though so if I go all the way to this viscoelastic picture, then I satisfy these strict contraction conditions, and I know trajectories meet. But then to get to Blake's question, you know, if I think about this vertical hopper system and I kind of do the mental simulation, or I just reason about the equations, you know, if I looked at potential plus kinetic energy, then if it's a spring damper and there's no external input, those things are decreasing in continuous time, and they're decreasing at the discrete time reset. So it really feels like the system should be contractive, trajectory should be getting closer because energy is dissipating. Now, so this is showing in one sense that our infinitesimal contraction conditions are a little bit more stringent than that kind of characterization of a system, like, you know, energy decreasing over time, because that energy decreases in the elastic limb as well as the viscoelastic limb. But a case where our analysis applies that just purely reasoning about energy, it's not obvious how to make it work in these piecewise systems, is that we can have, in parallel with this spring and viscoelastic damper, an actuator. So we can be injecting, with a time varying control signal, we can be injecting energy into the system. So then in that case, you know, energy is being dissipated by the damper, but it's being injected by the by the actuator. So it's not obvious whether there would be a steady state behavior or what it would be. But we're able to prove for this class of models that there is a steady state behavior and everything is converging to it.
And it looks like we have a question from Professor John Smith. He said,
oh, yeah.
Define viscoelastic.
Yeah, viscoelastic. So I was taught these things by a fantastic WRF funded postdoc I had, or UN funded postdoc I had, Tom Libby. I was a genuine full-on mechanical engineer. So my understanding is that by viscoelastic, really what we mean is putting a spring in series, a massless spring in series with a damper. And there are a couple of different standardized models that I'm aware of for viscoelastic elements. So you might have heard of MCK systems for elastic models. And so the kind of analogous terminology I'm understanding for viscoelastic are Zener models. And there's another name and I'm forgetting, or Voigt. Yeah, Voigt and Zener. So if you go to Wikipedia and you do viscoelastic and you do Voigt and Zener, you'll turn up some of the basic references that talk about these things. Okay, fantastic. Thanks so much for the questions so far. Now I'm going to switch gears and talk about our work modeling human-in-the-loop control systems. I'm going to go a little fast. I want to make sure that I end by no later than 11:25 to respect people's schedule constraints and things like that. But I'm really excited about this work, and I want to share it and be able to give it significant airtime. So our work is building on a paradigm that's dates back decades. So McRuer is one of the big names, aerospace researcher in like the 60s. And basically we're gonna plop somebody at a computer console, a pilot console. They're going to have one or more kinds of inputs they can apply to a system, like a joystick or some fancier inputs I'll describe in a second. And then we will display information to them on a computer monitor. This is a schematic from a 1959 paper where they do this. There was literally like an O-scope that's being used to display pictures on the screen and things like that. We just have a more modern digital version of this setup. And as I said at the beginning, I'm a control theorist. And so I look at that system, that physical setup of the person, trying to pilot something, play this little video game, twiddle the joystick, make the screen do what they want it to do. I view it like in the form of a block diagram. And as a control theorist, my big question here is what's inside H? What is the human doing? What is the transformation they implement between error signals from where they want to be and where they are, R minus Y, and possibly just looking directly at the reference that they're trying to track to their output, and then how does that behave in closed loop with the machine dynamics that we're prescribing? Now, in terms of hypotheses about what might be inside that human block, there's actually a lot of literature to draw on. Outside of control theory, the neuroscientists, sensorimotor control people have been thinking about this for a long time, and they have this very reasonable hypothesis that, okay, probably somewhere deep in the person's, cerebellum or motor cortex or other parts of the brain that I don't even know what they do, they learn some model of the system that they're working with. Let's call that a system model or a forward model. And then they invert that model in some sense to control it. So basically that says they see what they want to do, Y, and then they choose their input to do it according to the model that they've internalized. And the reason this is a particularly appealing theory of motor control for our work is that it has really strong parallels in the engineering and other kinds of mathematical circles, that I run in. So strong parallels in adaptive control, concepts like the internal model principle, reinforcement learning is very compatible with this picture as well. And so just one tweak I'm going to make is that I'm not going to call this an inverse model and empirically it bears out that people don't exactly invert the machine dynamics that we're displaying to them. They do something approximately like inverting it. And so as a proper control theorist, I'm going to refer to that as a feed-forward component of the human's controller. So returning to this block diagram, basically what we're doing is we're hypothesizing that inside that block, there is some kind of structure that has a feed-forward control term that depends solely on the reference that we're prescribing for the person to track, and then a feedback controller that operates on the error between the reference they're trying to track and where they actually are. And what's really fantastic about these block diagrams in control theory is that they're not just pretty pictures. If I hypothesize that, or if I impose that the machine that I'm making the person interact with is a linear time invariant system, then there's actually a lot of empirical evidence to show that the human block will converge to a linear time invariant system or something that approximates that, which means that I can do block diagram algebra. I can transcribe this block diagram into an equivalent set of equations and then manipulate those equations to try to, in an effort to determine these F and Bs that I cannot directly observe, but I hypothesize exist and I would like to estimate. So just really quickly, I don't have a lot of time and I don't want to bore you by spending the whole time walking through equations. The powerful thing about bringing these control theory methods to bear on these problems with humans in the loop is that we can take our block diagram, transcribe it into equations, and then manipulate the equations to get formulas that provide estimates for unknown, not directly observable quantities in terms of things that are totally directly observable. So HUR, HUD, these are the empirical transfer functions, the human implements, empirical transfer functions of the transformations the human implements from the disturbance signal that's coming in to their output U and the reference signal that's coming in to their output U. So those are things we can measure, and then we can do these manipulations, you know, in software to estimate these Fs and Bs. So the kinds of task and experiment that we do is we sit people down and they play a little video game where there's a reference in gold that they're trying to track, and they're providing some input by a little one-dimensional joystick, and then that's determining through some machine dynamics the location of a cursor, purple cursor on the screen. And they're just told, track the reference as best you can. What's invisible here, so you see the reference and it's wiggling. What's invisible here is that we are also bombarding or perturbing their input with an external disturbance. So that's contributing to tracking error as well. And so some of our initial findings were basically just reproducing known results from the literature, this deep literature that goes back decades. That, for instance, if I looked at the feed-forward and feedback controllers that I estimate from the person, the feed-forward model looks quite a bit like the inverse of the system model that I prescribe. So if I prescribe a first-order system model, meaning the person's commanding the velocity of the cursor on the screen, then across a range of frequencies, they approximately invert that system. In their feed-forward term provides an approximate inverse for that system. It's better at lower frequencies, and that performance kind of degrades as you increase the frequency. Similarly, if I prescribe a second-order system, so this is like prescribing acceleration, but there's just a little bit of damping in the system as well. Then same story, the person can more or less learn approximate inverse for the system. So these results are more just kind of validating the methodology and comparing it to prior results, but it's not really like our new contributions and the stuff that we're super excited about. So now I want to jump to those things. First experiment that I think is really, really cool result. The student, my PhD student, Momona Yamagami, is the one that's really leading the charge on these things. She took this basic paradigm that we developed through collaborations and kind of looking at the literature, and she's just run with it and taken it to all these exciting new directions that I never would have even thought possible. And so one of the first ones was applying it to different input modalities. So rather than just a joystick slider input, now we're equipping the person with a neural interface. Okay, so it's surface EMG, we're measuring muscle activity, but it is a genuine electrical signal that's coming from the nervous system. So I'm doing neuroengineering as far as I know. So we do this experiment where they do the same tracking task with the little joystick and with the isometric contraction of their biceps and triceps, and then we enable them to control it. And the results, to me, have a very surprising component. So if we look at tracking error, which is the task that we're prescribing, right? We're saying make Y like R, then whether it's a first order system or a second order system that the person's trying to track through, they do basically indistinguishable in terms of tracking error with the muscle or the manual interface. And interestingly, there is a significant difference with the manual interface between first order and second order, but so like you do a lot better tracking with a first order system with a manual interface than a second order system, but we don't see that distinction with the EMG, although obviously the errors are much more spread out. But when we look at the inversion, so how well does the feed-forward model that we estimate for the person approximate the inverse of the system model, there we actually see that the person's doing a better job inverting the second-order system with the EMG input, which surprised me a lot, because the EMG signals, if you've ever worked with them or seen any of these data, are incredibly noisy. We have to aggressively filter them to make any sense of them at all. And so I assumed that the performance with that EMG thing would be just dramatically worse across the board. What we're seeing is, in fact, for a second order system, you're better able to learn and implement the inverse of the system. Now, given that they're doing a better job inverting, but that their tracking performance is comparable, that means that they must be doing a worse job implementing feedback with the EMG interface. So I'm not showing this result to say that, EMG is strictly better than manual across all contexts. What I think is cool about this, though, is that it highlights that different input modalities have different properties, and they could play different roles in our complicated system. So if I wanted to control my complicated firefighting robot, I may want to provide EMG interface to pull out the feed-forward component of the controls input of the human's input, and then mix that perhaps with a stabilizing controller, or I use a manual interface to get to let them do the lower level kind of reactive feedback or something like that. But just the fact that you get these different performance properties that are one's not strictly better than another, but they're distinct, and they would be better to you'd prefer to rely on them in different regimes, I think is a really exciting possibility. And these results were published in this year's CHI conference, which is a highly selective, one of these highly selective computer science conferences. Okay, and then the second and final experiment I'll talk about, so I just have a couple more slides of technical content. Another experiment that Momona led, and that was actually executed by a really fantastic ECE undergrad that we have working in the lab, Lauren Peterson, so just wanted to highlight her contributions, compared hand performance. So I'm sure that we're all familiar with the concept that we have a dominant and a non-dominant hand. I'm right-handed, most people are, well, 70% of people are, approximately another 20% are, or 15 or 20% are left-handed, and the rest kind of don't distinguish. And we know that there are differences in performance, and indeed the neuroscientists or motor control people have observed differences in feed-forward and feedback components of control when using different arms to do reaching tasks. So what we were interested in discovering is, okay, do we detect the difference in our little manual slider game trajectory tracking task? So we recruited 18, well, I say we, Momona and Lauren recruited 18 healthy subjects, split them into 2 populations of 9, and had them play the game. One population play the game first with their right hand, then their left hand, and vice versa for the other population. Otherwise, the experiment is completely identical. We just reverse the order in which you play with your hands. Okay, so what I'm going to show are how tracking error rolled out over time. So over trials, each of these trials is like 45 seconds in duration. So as the person's kind of playing the game. And we saw, okay, tracking error, when I start with my right hand, decreases over time. And so the first 5 trials have significantly higher error on average than the last 5 trials with my first hand. And then surprisingly, at least to me, that tracking error, that decreased tracking error, persists when I switch hands. I don't see a shift, a return to pre-learned tracking error, and basically what was learned after 30 trials persists with the second hand for the rest of the trials. Similarly, if I start with my left hand, I get a very similar kind of decrease curve with the first hand, and then that learning persists with the second hand. And so if you looked at like actual distributions of errors and things like that, I get a significant decrease in both populations with my first hand, and then no change when I switch to my second hand, and no change for the remainder of the trials. So what we observe, at least in this experiment, is that regardless of whether you're right or left-handed, your hands perform the same, and tracking transfers when you do this. And sorry, I should say about the experiment design, I'm talking about dominant versus non-dominant. Of course, you could be left-handed, so left dominant. It just so happened all 18 participants were right-handed, and so in this experiment, I'm conflating dominance with right-handed, even though that's not true for everybody in general. And then if we look in more detail at the controllers people learn, we see some interesting differences. We thought that there would be much more significant adaptation in the feed-forward controller, that people would be learning something and inverting something in the system dynamics. But in fact, we see like no change in the feed-forward controller, and instead we see all of the adaptation happening in the feedback controller. So this result surprised us because it wasn't really our expectation. We thought we would see much more interesting adaptation in feed-forward. So this also suggests kind of a pivot or a redirection of where we're going to focus our energy in the coming years, which is if we're designing interfaces and kind of flexibly trying to support people teleoperating complicated systems, we should worry more about, we may want to worry more about the assisting or helping them learn feedback control, for instance, to minimize the effect of disturbance or motor noise or things like that. Then we worry about the forward model that they learn and the feed-forward model they implement for the system. All right, so those were all of the technical results I wanted to present. I'm hitting my my timing target exactly. So as I said, I have these kind of 2 threads to my research program. I have roughly equal numbers of students that have been working in these areas up till now. And now the future work for me is really to try to bridge this gap and do experimental integration of these 2 threads and really try to do some interesting, science at their intersection. So for the people who are familiar with this program, my NSF career proposal that's, under review right now, pending, under review, the main thrust of that is to integrate these 2 different themes. So, fingers crossed that gets funded or something similar so that we can deliver on this vision in the coming years. So with that, I'd like to acknowledge, the contributions of just this huge array of wonderful collaborators I've had here at University of Washington, and people that I knew from grad school and postdoc and have met in the community, as well as the the support of the sponsors that have funded this research. None of this work would be possible without all of these wonderful contributions. So I'll be happy to take any more questions people have in the few remaining minutes.